All right, class, continuing from where we left off on the last video on octahedral electron domain geometries, uh, variations in bond angles, and multi-centered VSEPR models. We're going to pick up from there. We're going to talk about molecular polarity. Now, molecular polarity, in order to be successful at this, you have to be able to draw a Lewis structure. You have to be able to evaluate the bonds between the elements in the Lewis structure and assign whether they're nonpolar or just pure covalent or polar covalent. You also have to be able to apply valence shell electron pair repulsion theory to determine the three-dimensional geometry of the molecule. And we're going to apply all that information in determining molecular polarity. So molecular polarity in its simplest form is what you see in this slide, and that is we have hydrogen fluoride. Hydrogen is on the left, fluorine is on the right. Where the color is red, that's a high electron density region. Where the color is blue, that's a low electron density region. We've actually seen this before. And so we know that we should assign a partially positive to the hydrogen and a partially negative to the fluorine, because fluorine's more electronegative than hydrogen. It pulls the electron away from the hydrogen. We can also represent that as an arrow, where the positive tail is on the partially positive end and the arrowhead is on the partially negative end. This is also called a vector. So if you hear the word vector, it's showing that there's a force moving towards the direction of the fluorine. So this is an example of a polar molecule. And so what we have here is we have a linear molecule. It is polar because fluorine is more electronegative than hydrogen, so the bond is polar. But then when we combine the geometry with the bond polarity, we see that the molecule itself is polar, that it has a positive and negative end to it. So this is about the simplest of the polar molecules. So next we do another molecule, carbon dioxide. So we've done the Lewis structure over and over again. And just to refresh your memory, the Lewis structure for carbon dioxide, you would say that carbon has 4 valence electrons and oxygen has 16. And you would say that, oxygen has 6. Yeah. And we got 2 of them, so 6 times 2 is 12, and then 12 plus the 4 is a total of 16 electrons. And so, when we did the Lewis structure, it looks like this, and there is a lone pair here and a lone pair here, and then there's a double bond and a lone pair here and a lone pair here. So 2, 4, 6, 8, 2, 4, 6, 8. That's my 16 electrons. You know that oxygen is more electronegative than carbon, so we would have arrows pointing from the carbon to the more electronegative oxygen, just as they show here in this diagram. So we have polar bonds. There is bond polarity. The bond has a dipole moment. So what that means is there is a force from the carbon to the oxygen bond, and that has a dipole moment. There's a force moving towards this oxygen. There's a force moving towards that oxygen. So when we apply VSEPR, we know this is AB2 if you want to write it as that, or AX2 if you like that better, either one. But it shows that there's 2 bonding groups coming off the central atom. And when there's 2 bonding groups coming off the central atom, the way you keep those bonding groups as far away from each other as possible is you place them 180 degrees from each other. And so we've got the correct structure, molecular geometry here. And you can see that these bond polarity dipole moments cancel each other out. So the net change in the energy or the force is 0 because they cancel each other out. So carbon dioxide, even though it has polar bonds, the molecule is nonpolar. So the molecule does not have a dipole moment, and it is a nonpolar molecule. Now you say, why do I need to know this? Well, we're going to find out that water is polar, and so carbon dioxide does not dissolve in polar water. So nonpolar molecules do not dissolve appreciably in polar substances like water. So that's what you're trying to get out of this section is being able to determine bond polarity or molecular polarity based on bond polarity and geometry. All right, so now we're going to look at water. So water, we've seen this before. We've done the Lewis structure for it. You know that water, when you do a Lewis structure, it looks like this. And you know that oxygen's more electronegative than hydrogen, so the electrons are being pulled more towards the oxygen. That creates a dipole moment for the bonds themselves. So the bond is polar. It's a polar covalent bond. But then we have to apply the geometry. And the geometry classification for this is AB2, E2. So the electron domain geometry is tetrahedral. And so I would write an oxygen here, maybe a hydrogen here, and a hydrogen here. And then I know that there's a lone pair coming out this way, and there's a lone pair going back through the board like that. So we know this arrow's pointing this way, and this arrow's pointing that way. So that's the dipole moments for each of those bonds. Overall, there is a resultant force in this direction. So when we look at the bond polarity and the geometry, when we look at those together, we see that overall there is a force moving from top left to bottom right, and that is a dipole moment for the molecule. So this molecule is polar. So if you generate an overall dipole moment in the molecule is polar. So that's what we have here. H2O has polar bonds, and then based on the geometry, it supports this bent structure that we've talked about. And they do so they don't show the lone pairs here. That's why I drew it my way. But you can see this one's a little easier to see. Both these arrows are pointing in an upward direction. That's the dipole moment. So the sum does not equal 0. There is a force in the upward direction here. And all we do here is the cosine of the angle here times that force, and the cosine of this angle times that force, and that will end up with a resultant vector in this direction. So this molecule is also a polar molecule. So this substance has bond polarity, but it also has molecular polarity. So that's what you're trying to do here. You're taking Lewis structure, VSEPR, bond polarity, determine if the molecule itself is polar. All right, here's another example. This is for boron trifluoride. Boron trifluoride, again, doesn't follow the octet rule. That's one of the exceptions that we learned in the previous chapter, that boron is satisfied with 6 valence electrons. We know the fluorine is more electronegative in green here than the boron, which is denoted by this orange. And so we do have polar covalent bonds, and they are pulling towards the more electronegative fluorines. But when we do when we take the cosine of 60 degrees here and apply that force, and the cosine of 60 degrees here, when we add these two forces together, cosine of 60 times the force, cosine of 60 times the force, it's going to equal this one force on this axis right here. So they cancel each other out, and the sum is 0. So there's no dipole moment. So even though the bonds are polar, the molecule is nonpolar molecule. You know, another way you can do this if you're really getting lost is you can assign the partially negatives to the fluorine and the partially positive to the boron. That's the bond polarity. If there's no way to slice this, draw an imaginary line through the molecule, and if there is no way to slice it where it's strictly positive on one side of the line and strictly negative on the other, then it's a nonpolar molecule for the most part. Doesn't work all the time, But if you had to guess, think about this line method. I'd rather you think about it in terms of vectors, but if you're really struggling with vectors, what does polar mean? Polar means there's a positive end to the molecule, or molecular polarity means there's a positive end to the molecule and a negative end to the molecule. And if you can't get a strictly positive and strictly negative end, then it's probably a nonpolar molecule. Doesn't work all the time, though. All right, here we have carbon tetrachloride, and then we have methylene chloride. There's another. So let's look at these two to make a difference. Here. Let's see, is that right? Methylene chloride, or it's trichloromethane. That's it. That'd be. I know that one's right. Trichloromethane. Okay, trichloromethane. All right. So for this one, these are chlorines. And you know that chlorine's more electronegative than carbon. You know this is a AB4 VSEPR. It's 4 bonding groups coming off the central atom, so it's tetrahedral. So that's what we have here, 109.5 degrees between a chlorine, a carbon, and the chlorine. So 109.5. And again, what's happening here, all these forces cancel each other out. If I take the cosine of this, the cosine of that, and the cosine of that, it'll all equal to this, and times the forces, the overall resultant force is going to be equal to this force here on the axis. And so the molecule has polar bonds, but it is a nonpolar molecule. So you're going to hear it said this way. The bonds are polar, but when we apply VSEPR and we get a tetrahedral geometry, the molecule itself is nonpolar. The molecule does not have a dipole moment. Now, if we knock off one of these chlorines and then put in its place a hydrogen, well, now you can see overall all of these forces are going in this direction. If you add up all these downward arrows here, they're all going in one direction. There is a resultant force or vector in the downward direction. And so the molecule now becomes polar. So when they're all chlorines, they cancel each other out. But when we substitute one of the chlorines for a hydrogen, now the molecule becomes polar because the sum of all these vectors is not equal to 0. Whereas in this one, where they're all chlorines, they're all pulling equal and opposite, the sum equals 0, and that is a nonpolar molecule. I would look at this slide, make sure you understand this slide. I think this kind of really shows you, the difference between bond polarity and molecular polarity, and it is based on geometry. It's based on the forces, and for this one, the force isn't as great as that force there, and so therefore there is a resultant force in this direction. All right, here's another example, phosphorus pentachloride. All these forces cancel each other out. These are all in the equatorial position, and that they're like a triangle, and they just like boron trifluoride. Yeah, it's a terrible drawing, but they all cancel each other out, and then this one on the axial position cancels out this one on the axial position. So again, you have polar bonds, but based on the geometry, phosphorus pentachloride is nonpolar. All right, here's one that's a little trickier because we don't really see any lone pairs on the carbon. But what you do know is the double bond here. First of all, this is a polar bond, and it's a double bond. And the hydrogens are less electronegative than the carbon. So overall, there is a resultant force in this direction. And so the aldehyde here is a polar substance. Let's see, what's the next one? And we'll skip that. And all right, so this is really a good point to make in organic chemistry. So this is really important for organic chemistry. So when you take ethane, which is C2H4, that's ethane, and you substitute to the hydrogens and make it C2H2Cl2, you're going to get a mixture in the reaction where the chlorines are across from each other and they're beside each other. So if they're across from each other like this is called trans, like transatlantic across the ocean. And beside is called cis. And so when the chlorines, which are more electronegative than the carbons or the hydrogens, this is pulling this direction, this is pulling this direction, and these two hydrogens are canceling each other out this direction. The overall resultant forces cancel each other out. These two cancel each other out, and then these two cancel each other out. And so overall, this is a nonpolar molecule. Whereas when both chlorines are on the same side, you can see the resultant force is in a downward direction here, that there's a downward resultant force. So the overall sum is not equal to zero. So that means there's a dipole moment. We call it a resultant vector or dipole moment. And this molecule is polar. So this cis is polar, trans is nonpolar in this case. And you say, how am I supposed to know this? Well, when you draw the Lewis structure and then the VSEPR, you would figure out that there's two possible choices here. So these are called structural isomers. There's two ways to draw the same chemical formula. Structural isomers. Two ways to draw the same thing. So when you do this in an organic lab, what you can do then is you can pour this mixture into a separatory funnel. It's a special kind of funnel. Maybe you've seen one. It looks like a balloon of glass. It's got a little valve here that you can open and close, and then it's got the tip here. And then it's got an opening up here to pour your liquid in. So what you do is you'd pour water in here, H2O, and then you'd pour in your mixture of these two compounds. And then you shake it up and you vent it off, and so this mixture mixes with this one. Well, which one of these is going to dissolve in water? Which one of these two substances would dissolve in water? And you should say, oh yeah, it's this substance. Why this substance? Because it's a polar molecule. Like dissolves like. So this polar molecule is going to dissolve in the polar water. And so the water will contain the cis isomer, and then the rest of the isomer will remain in a different layer above it here, if it's lighter than the density of water, which it is. And so then you can drain off the water with the cis isomer, and then you can evaporate the water off, or distill if you want to do that. You could distill the substances, separate them that way. So that's the way a lot of times we use it. And that's why this is called a separatory funnel. We use this type of funnel to separate polar from nonpolar molecules. Great technique. So that, again, this is why you have to know this. This is not something we just go through. It is something you have to know. All right, so here is the ultimate test if you can put chapters 5, 6, 7 together. This is the summary. This is what we're shooting for right here. So you know from chapter 1 that some substances are solid at room temperature, some substances are liquid where the molecules are free to move around each other. They're not held in a fixed position. And then we have gases where each atom or molecule is acting independently. So the force between this molecule and this molecule, or this one or any other one, that's called an intermolecular forces or van der Waals forces. So right here, intermolecular forces are attractive forces between neighboring molecules. These forces are collectively called van der Waals forces. I want you to know this term here, van der Waals. So the magnitude of the intermolecular force determines whether that substance will be a solid or a liquid. And gases apparently have no intermolecular forces because they're acting independently. We assume in an ideal gas, each molecule is acting independently and it's not attracted to another molecule. All right, so that's what the focus is. Based on everything we know, we are now going to assign intermolecular forces to a substance, or the forces between two molecules of that substance, or all the molecules. So the first one is a dipole-dipole interaction. So what happens with the dipole-dipole interaction is that one, it says here, you got to read what the question says. It said red means high electron density, blue means low electron density. So red, partially negative charge, blue, partially positive charge. So this is partially positive on this end, partially negative on this end. We know that opposite charges attract, so notice that the partially positive here is attracted to the partially negative there. There's a force between these two molecules here. Or let's see if there's a good gap. There's a force between these two molecules. There's a force here. There's a force there. There's a force there. There's a force there. There's a force here. Notice both of those to the same one. This is here. This is here. This is here. So it is a force between the molecules, and it's not so strong in a liquid that they can't move around each other, so they have the ability to flow. But in a solid, they're very rigid. It's negative, positive, negative, positive. And again, partially negative, partially positive. I'm just not putting that in there. Negative, partially positive, and so forth. So the stronger the intermolecular force, the more likely you're going to have a solid. The weaker the intermolecular force, the more likely you'll have a liquid. And if you don't have any intermolecular force, then you have a gas. So notice, like right off the bat, the strongest force is going to be ionic forces, like between sodium and chloride. That's why most of your ionic compounds are solids at room temperature. But a lot of your strong things that have strong intermolecular forces, like let's say, trying to think of one off, like yeah, I can't think of one right off the top of my head. Oh, I should know one off the top of my head that's really easy. Well, let's move on. I'll think of something here that'll give us an example. But again, even water is not a solid at room temperature. It's a liquid. But we freeze it down to 0 degrees Celsius and it becomes a solid. And the intermolecular forces come into play here. So we'll see more examples. I just can't. I'm having a brain lock here. All right. So here, let's look at this. This is a list of molecular compounds. And so we know that room temperature is about 25 degrees Celsius. So at 25 degrees Celsius, these definitely, look at their boiling points. They're so low. All of these are going to be gases at room temperature. If room temperature is 25 degrees Celsius. Acetonitrile will be a liquid at room temperature because its boiling point isn't until 82 degrees Celsius. Well, that kind of makes sense, right? Let's look at acetonitrile. It looks like this. There's a triple bond to, let's do it differently. So first of all, this part is going to look like, and this is where all this comes into play, what we've been doing. So off this first carbon, that's AB4, and it's these three hydrogens attached, and then a carbon attached here, so I got a solid line there. And then on this nitrogen here, you have a triple bond to a nitrogen, and that makes your 4 bonds there. So this is like AB2, right? AB2, so that'd actually be linear from this point. And so this is going to be partially positive here, partially negative here, and that's going to create a dipole moment there for the molecule. So because this has a dipole moment, if there's another one in close proximity, it's probably going to be attracted to one of those carbons, and you're going to see intermolecular force between this nitrogen and the carbon of another compound, of another one here. Maybe it's here, and maybe you have that down here, and then you've got a hydrogen and a hydrogen coming out of the board, and hydrogen going back through the board. So there's an intermolecular force between this molecule and this molecule. And the type that's going to occur between these two is a dipole-dipole interaction, because you got a dipole here and you have a dipole here. This partially negative is attracted to the partially positive of that carbon. It's not a true bond, it's just a force of attraction. Whereas when you have propane, propane looks like this. It's 3 carbons and then the hydrogens are coming off, and you don't have to draw them all. In fact, a lot of times this is the simplest way to draw it. Or the simplest way is to just go like that. There's propane, where each one of these endpoints is a carbon, and anywhere you have a point like that, it's a carbon. So that's 3 carbons long, and we would assume there's 3 hydrogens coming off here, there's 3 hydrogens coming off here, because carbon follows the octet rule, and that means there has to be 2 hydrogens coming off here to get that carbon for 4 pairs of electrons, or an octet. So you're going to see structures like that, but again, there's no dipole moment here. This is a nonpolar molecule, and so the dipole moment is very, very, very small. I guess there's a small dipole moment just because of the difference in carbon and hydrogen and the structure. But look at its boiling point, negative 42 degrees Celsius. I mean, that's definitely a gas at room temperature. You know it's a gas. Propane grills, you open the valve, it's a gas at room temperature. The dimethyl ether, it's got a carbon down to an oxygen, back up to a carbon, and then there's 3 hydrogens coming off. So there is a polarity here, and there would be a resultant vector in this force, and so that's why it jumps up to 1.3 here. The methyl chloride, we've already seen that. That's looks like this, and then it's got the hydrogen here and a hydrogen here and a hydrogen going back like that. Well, there's definitely a vector in this direction, so its dipole moment's 1.9. Acetaldehyde, which you have carbon. I am running out of room. It's carbon double bonded to an oxygen, a hydrogen coming off this end, and a CH3 group coming off this end. So it's acetaldehyde. So, and again, you've got definitely polarity here, and that's going to create a dipole moment for the molecule of 2.7. So you can see that as the dipole moment increases for the molecule, so does its boiling point, because the attraction is greater. You have to break that attraction to go from a solid to a liquid to a gas. So a special type of dipole-dipole interaction, this is really important. If you're going to remember any one of these intermolecular forces, this is the most important one in biology and chemistry, and that is the hydrogen bonding. So hydrogen bonding, it's not true bonding. What it is, it's when hydrogen is bonded to one of 3 elements. So here we see a solid line. This is the hydrogen in blue at this end, bonded to a fluorine here on the red. Remember, this is electron density. This is electron rich. This is electron poor. So hydrogen bonding is the intermolecular force between one hydrogen fluoride and the next hydrogen fluoride. So we're comparing this molecule, hydrogen fluoride, to this molecule. And the intermolecular force, the force between them, is this dashed line right here. So that dashed line represents hydrogen bonding. It's a special type of dipole-dipole interaction. It's stronger than just your average dipole-dipole interaction. But it can only occur when hydrogen is bonded to one of these 3 elements, nitrogen, oxygen, or fluorine. If hydrogen is bonded to anything else, hydrogen bonding does not occur. So when we look at ammonia, hydrogen is directly bonded to the nitrogen. We got a lone pair here. So if we had another ammonia in close proximity, there would be an attraction between, what do I want to do here? I could draw it like this to make it a little easier. And then there's a lone pair there like that. There would be an attraction between this nitrogen and one of those hydrogens there. That's the hydrogen bonding. All right. So hydrogen has to be bonded to either nitrogen, oxygen, or fluorine, and the intermolecular force between the two molecules is called hydrogen bonding. I hope I stressed that enough. You can see it here. It's the dashed lines. We call it hydrogen bonding, but it is an intermolecular force between the molecules. It's not like a true bond. It's not where we have hydrogen bonded to fluorine, which is represented by these solid lines here. It's a dashed line to another hydrogen fluoride. That's the intermolecular force called hydrogen bonding. You go, why do I need to know this? This is what holds your DNA together. So compounds that break the hydrogen bonding in the DNA, they tend to cause mutations. And so that's why we're always concerned about certain chemicals getting into our bodies, because it may damage these hydrogen bonding sites and therefore cause mutations. So hydrogen bonding, it's a little bit stronger of a force than a dipole-dipole interaction. And here's an example. Let's look at the trend here. And this is a really neat chart to look at. So what you see in this chart is water has a lot of hydrogen bonding. And you think, what? Let's talk about water. Hydrogen is bonded to oxygen. And then there's a lone pair here, and there's a lone pair here. So another water molecule in close proximity at low temperatures, in the solid or liquid form, this hydrogen is attracted to those electrons there. We could have another hydrogen attracted from a water molecule to this pair of electrons. Then we come down here, and here's a water molecule, and that causes an attraction, the lone pair there. And then we have another water molecule with the lone pair and a lone pair, and a hydrogen here and a hydrogen here, and there's an attraction there. So what's cool about water is it forms up to 4 hydrogen bonds. And because it has so many hydrogen bonds, that's why its boiling point's 100 degrees Celsius, which is really strange. Think about it. Let me show you how strange this is. If we substitute sulfur for the oxygens, the boiling point for that's like, negative 60 degrees Celsius? And water's 100 degrees Celsius. So that's how powerful hydrogen bonding is. This should have a higher boiling point. Sulfur is heavier than oxygen. So if all things are equal, the one with the greater mass should have a higher boiling point, because it takes more energy to get it kinetically energized to escape as a gas. But in this case, water is huge compared to hydrogen sulfide. Hydrogen sulfide's that smell, you get a rotten egg smell around a sewer plant or something. That's the hydrogen sulfide smell. So that's how big a difference hydrogen bonding makes. Here's HF, hydrogen fluoride. Again, very light molecule, but it has a boiling point above 0 degrees Celsius. And then hydrogen chloride, look at its boiling point. Again, negative 70 or 80 degrees Celsius. Here's ammonia. Hydrogen bonding occurs here. So there's N, there's F, there's oxygen. So nitrogen, fluorine, oxygen. And again, right next to it, phosphorus, or phosphine, or you could call it phosphorus trihydride or phosphine. It's got a common name, phosphine. So look how much less it is. Just because it doesn't have hydrogen bonding, even though it is heavier and it should require a little more energy. And then this group here, no hydrogen bonding here. So that's why methane here, no hydrogen bonding. The only force that's happening here is London dispersion forces or instantaneous dipole, which we'll talk about in a minute, but not much attraction between molecules for just hydrocarbons. So important chart, you might want to look at that, try to figure it out, understand why the top three here are due to hydrogen bonding. All right, London dispersion forces, also called instantaneous dipoles. You need to know both terms that they mean. So here's different names for the same thing. I think that's what throws students off. Dispersion forces, London dispersion forces, an instantaneous dipole. All of these occur for nonpolar molecules. And you go, what are they talking about here? Well, let's take something really simple like helium. You've got a helium atom here, and you've got a helium atom here. Now, helium can be compressed and cooled to be a liquid. I mean, normally you think of helium in a helium balloon, but we do have tanks of helium that is compressed and it is in the liquid form. Well, how do they attract to one another? If there's no attraction between the helium molecule or atoms whatsoever, then it should always remain a gas. It should never become a liquid or a solid. So how does one helium atom become attracted enough to another helium atom for them to stick together and form a liquid or a solid? Well, here's what it looks like. Let's say that this is a helium atom and this is a helium atom. And what happens is at any given time, the two electrons in the helium are over on the upper left-hand side here of the helium atom for just a second, less than a second, right? Well, when that happens, this side of the helium atom becomes partially negative and this side becomes partially positive. And when it's close to another helium atom, when it's really, they can't move much, very cold temperatures, this side will become partially negative because the electrons of the helium are going to be attracted to the partially positive side of this helium, and that's going to make this side partially positive. And so there's an orientation here, partially positive, partially negative. This is negative, remember, this is partially positive. And that's called an instantaneous dipole. Now, given a few seconds later, that instantaneous dipole is gone, but other instantaneous dipoles have been created. So when a substance causes a dipole to occur in another substance, that's called an induced dipole. It causes this side to become partially negative and this side to become partially positive. So it's an induced dipole. We call them instantaneous dipoles. And that's enough energy under high pressures and low temperatures to get the helium atoms to stick together enough to become a liquid. Without any attraction whatsoever, you can only have a gas. But here, because there's an instantaneous dipole, it does cause an attraction under certain conditions, and we do get the condensed phases of a liquid or a solid. All right, that's an important one, dispersion forces. So that's what they're showing here, is that if you got two of the same atom bonded together, there's no dipole moment for the molecule. I mean, they both have the same electronegativity. They're both pulling equally as hard for the electrons. And so there's no partial negative or partial positive end. So the only thing that can happen is at any given time, there's more electrons on this side than there is on this side. That creates an instantaneous dipole. And so notice the really low boiling point for fluorine. It's a very light molecule. It only has dispersion forces or London dispersion forces or induced dipole forces, if you want to say that, or instantaneous dipole. That's why it's a gas at room temperature. This is a gas at room temperature. Now, you say, well, what about bromine? Bromine would be the same thing, right? It'd be a bromine bonded to another bromine. But this is not a gas at room temperature. It's a liquid. Why is that? Well, if all things are being equal, this weighs a lot more than this. And these are larger atoms than fluorine. So what happens is the larger the atom, the more the electrons can become separated. We call it polarizability. And the more polarizable the atom, if all things else are equal, the more likely there'll be a stronger instantaneous dipole. Now, we can do it by molar mass here. In fact, that's the way this book works. They say all things being equal, as the molar mass increases, so does the boiling point. And that'll work for you. That will work for you. All right, so here's your test. Here's your test right here. After talking about dipole-dipole intermolecular forces, special type of dipole-dipole called hydrogen bonding, and then dispersion forces, which are instantaneous dipoles, be able to label the types of intermolecular forces that exist. Okay? So it says what kinds of intermolecular forces exist. Yes, you have to draw the Lewis structure. Yes, you have to apply VSEPR. Yes, you have to evaluate the bond polarity. And ultimately, you're going to use the VSEPR and the bond polarity to determine molecular polarity. Once you get the molecular polarity, you're going to think about what type of force then. Is it dipole-dipole? If hydrogen's attached to either nitrogen, oxygen, or fluorine, then you know you're going to have hydrogen bonding. And then if there's no dipole-dipole and there's no hydrogen bonding, then the only thing it can be is dispersion forces. So, what do you think about the first one there? Well, you should automatically say, I know chlorine is more electronegative than carbon, so you know that. The geometry for this, the classification is AB4. If it's AB4, it's tetrahedral. That means there's a carbon here, there's a chlorine here, there's a chlorine here, there's a chlorine coming out the board at you here, and there's a chlorine going back through the board. And so if I look at all these vectors, the molecule itself is nonpolar. So if the molecule is nonpolar, then let's look at the answer here. So carbon tetrachloride is nonpolar, so the only intermolecular force would be dispersion forces. So draw a circle around this. This is one molecule. If you had another molecule of it right here, because this is nonpolar and this is nonpolar, the only thing that causes these two things to stick together is dispersion forces, or London dispersion forces, or instantaneous dipole. You could say it any of those ways. Okay, let's look at the next one. Well, the next one, you have carbon attracted to that oxygen, and that's going to, and if you know, again, what do you do here? Do you have to draw this all out? Maybe not, but I think it helps if you can. So this is what this substance looks like. And so you have a dipole there, right? Positive and negative. You actually have a dipole here as well. And then here you go, oh yeah, that's a dipole. It's going this way. But then you know that's bonded to the hydrogen's bonded to the oxygen. So, and then over here you got dispersion forces on this side. So that's what's cool about these big molecules. You're going to have areas where you have dispersion forces here. You're going to have dipole-dipole forces between this and another molecule here, and you're going to have hydrogen bonding in here. Like if there's another one of these molecules, this hydrogen is going to be attracted to the oxygen of the other molecule. So B has it all, right? B has dispersion, it has dipole, and it also has hydrogen bonding. So let's just make sure. So right here, if you look at your answer, you can see that the OH bond's present, so that's hydrogen bonding. The dipole-dipole exists between the carbon and the oxygen, and there's dispersion forces with this part of the molecule here. So dispersion, dipole is possible with another one of these nearby, and then we have hydrogen bonding that can occur to another molecule somewhere else. All right, let's just stick to this page. What would you see for this one? On this one, you see dispersion forces here between this and another molecule. You'd have dispersion forces here between this and another molecule. And then you'd have a dipole interaction here with another molecule. Maybe like there's another one of these molecules right above it. There would be an attraction, and then there's a double bonded oxygen here. There would be an attraction between this partially positive carbon, this partially negative oxygen. So it is polar, does not contain nitrogen, fluorine, or oxygen bonds. Notice the hydrogens are bonded to the carbon, not the oxygen. So it exhibits dipole-dipole interaction right here between this one and another molecule. And it also has dispersion forces. All right, now this one's tricky. When we draw this structure, they talk about it in the book, and it actually comes out to be more like this instead of water. It's almost a 90-degree angle between the hydrogens and the sulfurs. And sulfur has an electronegativity of 2.5, and hydrogen's 2.4 or 2.1. A difference of 0.4. It's slightly polar to the sulfur, but then you have these lone pairs here too. So there's a little pull this way towards the lone pairs. Overall, there's a resultant vector force in this direction. So you're going to have dipole-dipole because of that between this molecule and another molecule, and you're also going to have dispersion forces. This one's a little tricky. They talk about this in the book. You may want to read that this one doesn't follow the hybridization model of bonding, which we haven't talked about yet. It follows more like a valence bond model. So it's not like water, which is 104 degrees between the two hydrogens, and the lone pair is out here, and there's a lone pair out this way. But this is 104. This is more like 104.5. This is more like approximately 90. So if you have to guess a force, always guess dispersion. I mean, unless it's ionic, dispersion forces happen. But the other forces are the ones that are really, you want to focus on too. Dipole-dipole or hydrogen bonding. But hydrogen bonding can only occur when the hydrogen is directly bonded to either nitrogen, oxygen, or fluorine. Can't stress that enough. All right, last of our forces, ion-dipole interaction. This is how table salt is able to dissolve in water. So water is not ionic. This is partially negative oxygen. These are the partially positive hydrogens. Well, these partially negative oxygens can surround the sodium ion that creates a cage around the sodium ion. We call it hydrolysis. And that's what separates the sodium ion from the chloride ion. So you have a chloride ion down here. All the partially positive hydrogens orient themselves towards the chlorine. And so that creates a cage around that, and they can't get back together, and we see it as dissolving. That's coming up, so that's why Again, this is why this is important. This is why we're talking about it now, because in the next, maybe not the next chapter, the chapter after that, we're going to talk about why does sodium chloride dissolve in water, but calcium carbonate doesn't. Um, well, one thing is, you would think calcium carbonate, because it has this, calcium's a 2 positive ion. And again, we know by point charges, Coulomb's law, that if this is positive 2, and this is a partially negative 1 on this oxygen, there's going to be a stronger attraction between this than a positive 1 here on the sodium and a partially negative charge on the oxygen. So this is a weak interaction because this is a positive working with a partially negative negative value. This is a positive 2, larger positive ionic charge, and this is still a partially negative 1. So yes, this is a strong interaction. This would be a weak interaction. So that's called ion dipole. So ion dipole, really important when we talk about ionic substances dissolving in water coming up. And it is the partially negative of a molecule attracted to the positive charge of the ion, or it could be the opposite like we have here, the negative ion attracted to the partially positive charges of the hydrogen. All right, so in summary, we have van der Waals forces. Let's go back to that slide. So van der Waals forces is just another way to say intermolecular forces, okay? And they're attractive forces between the molecules, and the choices are ion dipole, dipole, where we have we have polar molecules, polar bonding, and we get this dipole interaction. A specialized type of dipole interaction called hydrogen bonding. And then if we don't have a dipole or we don't have hydrogen bonding, then it has to be dispersion force or instantaneous dipoles or London dispersion forces. All 3 of those words are used, so you have to know all 3. And if all things are being equal, then molar mass becomes the factor that contributes most to intermolecular attractions or forces. So it'd be dispersion, and then the intermolecular, that would be the intermolecular force, but then mass comes into play there. Be able to identify the types of forces in a molecule, you have to do a Lewis structure, you have to do a geometry, and then you have to think about bond polarities and so forth. And then ion dipole interactions. All right, so that's where we're going to stop with this video. I hope this helps. I think that gets through most of what we need to cover. The other things I want to talk about is valence bond theory, just a little bit about it, more just about optimum overlap between why is it. Valence bond theory is going to explain why it's only the outer shell electrons are involved in a chemical bond. And then we want to talk about a little bit about hybridization. I'm not going to go too much detail into it. I just want you to really look at I think it's table 7.7. If you know the classification of the molecule, then you will know the type of hybridization that occurs. So that's what the focus is on that. So hopefully that helps. And if you need additional instruction, just email me.